This video is inspired by an article on 538 called How to Tell Someone's Age When All You Know Is Her Name. And it turns out you sort of can, right, predict somebody's age based on their names. But with some names, you can be a whole lot more accurate than others. So like this little graph is showing for the name Anna, you can't be very accurate in your predictions because Annas have a huge spread of ages. Whereas if somebody's name is Jennifer, you can be a little bit more accurate if you were to try to predict that person's name. My favorite observation about this comes from the show Unbreakable Kimmy Schmidt.
Well, I wasn't expecting this meeting to happen till tonight, but Titus, I'd like to introduce you to Linda.
Oh, who's Linda? Your mom's friend? A woman you bought a funky lamp from on Craigslist?
No.
My daughter, Linda. Wow. Your baby's name is Linda, Kimmy. He named his baby Linda. That's not a baby name. That's a name for an adult woman who works in human resources and says stuff like Mondays.
The show is so good. Also, the same episode has Daveed Diggs in it, so definitely watch it. But let's get back to Titus's idea. What would we predict about somebody if we knew that her name was Linda? So we're going to look here at the distribution of ages for women named Linda. So you can see in this picture, it says the median living girl named Linda was born around 1953 and ranges from 58 to 70 years old. So yeah, not a baby name. We're going to go a little further and describe this distribution in terms of shape, center, and spread. So let's start by just looking at a few different shapes that a quantitative distribution could have. So you could have this nice bell-shaped distribution, right? This has sort of just the one peak in the center, pretty much symmetrical, and then it tapers off as it goes to the sides. You could have one that's not symmetrical and the hump is on one side. So like here, we have the hump on the left side and then a long tail on the right side. That shape is called skewed right. And of course it could also be skewed the other way. Maybe it looks a little bit different. Maybe it doesn't have the hump. Maybe it just kind of steadily goes up that way. This one would be called skewed left. And I always remember it that like if you look at your feet, your right foot looks skewed right and your left foot looks skewed left. So all three of these pictures, these all have only one peak. And so we're going to call these unimodal. So the mode is the peak and it only has one, so it's unimodal. The other shape that we could get is maybe something has multiple peaks. So something like that we would call bimodal. So looking at this distribution of birth years for people named Linda, I would say that this distribution is skewed to the right. It's got one peak and then it tapers off with a long tail on the right side. So in recent years, there have been babies born named Linda, but not too many. So what if we want to talk about the average woman named Linda? For that, we're going to need measures of center, and we're going to talk about two different ones. One is the mean, and the mean of this data is 64 years. I'm not going to show you how to calculate it because I think you know. You would just add up all of the ages and then divide by the sample size. So that's the mean. Another way that you can think about the mean is that it's like the balance point of the distribution. So you can kind of imagine if you take this distribution of women named Linda and you were to stick a balance somewhere, where would the weight level out? That's another way to think about the mean. The median age is another measure of center. The median here is 67 years old. So one way that we can think about this is that it's the age of a typical Linda. So we use the median to describe the typical value because the mean can be pretty sensitive to outliers and skew and things like that. The median not so much. So it's a good measure of sort of a typical value. But technically how we interpret the median is it's the point that splits the data set in half. So if your median is 67 years old, that means that 50% of your living Lindas are younger than 67 and 50% are older. So it's splitting the data in half. 50% younger than 67, 50% older. So those are two ways of measuring the center. What about the spread of this distribution? So this is another way of thinking about if you were trying to guess this person's age, how accurate could you be? Because how spread out are these people? So we're going to again talk about two different measures of spread. One is the standard deviation. So the standard deviation is 10.95 years. And I think it's a little bit difficult to think about the standard deviation from that graph on the left because we can't see the individuals. So let's look at this graph over here. So here I have a graph. This is 100 people named Linda, and I'm looking at their ages on the graph here. So if you think about finding the mean, which in this case was 64 years, right? There's our mean. And we can think about how far are the data points from the mean. So we can look at people who are a little below or a little above and think about finding the distance from these people to the mean. So these distances between individuals and the mean, those are called deviations. So then a standard deviation is sort of like the typical distance from the mean, right? How far do we expect an individual Linda to be from the average of 64? So if we interpret the standard deviation, we would say that the typical distance from the mean, in this case, is 10.95 years. So that's our standard deviation. So that's a measure of spread in terms of distance from the mean. Another way I like to think about it is in terms of accuracy. So let's say you were trying to predict this woman's age. So if you guess that Linda is 64 years old, that's the mean, how far off are you going to be? If you guess 64 on average, you'll be off by 10.95 years. So that's another way to think about the standard deviation. The interquartile range is another measure of spread, but the way that it's calculated is totally different from the standard deviation. It's actually more like the median. So the median divided the data set in half. Now let's imagine that we're dividing the data set into quarters. So Q1, or the first quartile, is 58 years old. And this means that 25% of Lindas are younger than 58 years old. Younger than 58. And then on the other side, Q3, or the quartile, and then on the other side, Q3, or the third quartile, is 70 years old. And so that means that 25% are older than 70. So if we want to find the interquartile range, we're finding the distance between those two. So we're taking 70 minus 58, and that gives us the interquartile range. So whereas the range would be like all the way from the minimum age to the maximum age, the interquartile range only looks at that middle 50%. So this is telling us that the range of the middle 50% is 12 years. Range of the middle 50% is 12 years. And the first and third quartile actually were given to us up here under the graph. Okay, so when we go to describe a distribution of quantitative data, those are the things that we want to think about: shape, center, and spread. And we want to be able to choose appropriate numerical summaries.